Okay, good morning, everyone, to another Earth Institute coffee morning. It's great to virtually see you all. So this morning, we're going to have a talk by Dr. Shen Wang from the School of Computer Science, where he's going to be talking us about more sustainable and resilient urban traffic using connected and autonomous vehicles. So I'm really interested to hear how my car is going to drive me around Dublin in the future. Thanks very much, Shen. You can give your talk now, please.
Thank you, Connor, for your introduction. Hello, everyone. I'm Dr. Shen Wang from School of Computer Science. This is the first time for me being with you guys on a coffee morning hosted by Earth Institute. So the short talk I'm going to make today is about more sustainable and resilient urban traffic using connected autonomous vehicles, CEV for short. Okay, firstly, let's have a quick recap of what is sustainable traffic. So this is the United Nations Sustainable Development Goals. It was released in the year of 2015. It composed of 17 goals. So for sustainable traffic, it is more about achieving the number 3 goal, good health and well-being. Number 9 goal, industry innovation and infrastructure. And number 11 goal, sustainable cities and communities. So UN set this goal about 2015, the year 2015, and hopefully we can achieve these goals by the end of the year 2030. So in particular, for sustainable traffic, on the 3rd Sustainable Development Goal on health, which includes a target addressing death and injuries from road traffic accidents. For the number 9 goal on infrastructure, which includes targets on developing quality, reliable, sustainable, and resilient infrastructure. And for the number 11 goal on sustainable cities, which includes a target on providing access to safe, affordable, accessible, and sustainable transport systems for all, and on expanding public transport. So all in all, sustainable transport is one of the major components of all 17 goals that is set by UN SDG. Okay, now having known about sustainable transport, what is resilient transport? So please look at this little figure on your left-hand side. On the horizontal axis is time. On the vertical axis is operational level of the transport network. So normally, the operational level of the well-designed transport network will operate as normal until a disruption happens. For example, the en route event, like car crash or something like that, that leads to road closure. Then the operational level of the network will degrade for a short amount of time. This is the impact of such disruptions. And then if the network is designed inherently with some certain level of resilience, it will recover back to its normal level. So this phase is called resilience. The shorter, the better. The other interesting example to show here is to compare the two network designs. Suppose that we all have these requirement like 5 nodes, and how are we going to distribute the edges? So one solution is the efficient solution, is that okay, we will distribute 4 edges. Each edge has a decent amount of throughput, and it's well connected, and it has high throughput. The other solution is called resilient, which means that we still have 5 nodes, but we'll have more edges. But for each edge, it has much less throughput, but more resilience, because let's take this as an example from A to B. So in a normal time, if you want to deliver something from A to B, you will go from here, right? But if this edge goes down, then for resilient network, you will still have multiple choices to go through. But for efficient network design, once this edge goes down, then it's completely disconnected. So this is the second interesting example to show you how resilience is important for designing a good network, transport network. Okay, so knowing about fundamental concepts of sustainable and resilient transport, let's look at what is the problem of the existing urban roads traffic. The first problem is the emissions problem. So out of all global CO2 emissions, transport accounts for almost a quarter of that, the emissions from energy, and out of all transport mode, nearly 3/4 of the transport emissions actually comes from the road vehicles. So that shows how important it is to reduce the emissions on the road traffic in order to achieve sustainable development goals. The second problem is the safety problem. This is not a very up-to-date statistics, but from these two tables that you can see that out of all transport modes, rail, air, ferry, and road, the road transport accounts the highest percentage of the death per 100 million person kilometers, and also travel hours. So it is dangerous actually. And the third problem of designing the urban road traffic is how to alleviate congestions caused by en route event. So we're talking about these type of congestions. So it is unlike the recurrent traffic congestions that happen every day due to daily commuting, because for that kind of congestions, it is predictable using big data and AI technologies. For these kind of congestions, such as this temporary road closure, it is difficult to predict. And once it happens, it really needs a very timely response. So to achieve the higher resilience level of the whole transport network. Okay, now, before we go into details about connected autonomous vehicles, let's look at why the traffic waves happens. So this is a very interesting field experiment in which that you will have, you will look at this ring-shaped road. All the cars are human-driven cars, one followed by one another. At the beginning, the gap are all evenly distributed, but after a very short amount of time, because the delayed human-driven behavior response, then you can see the gap becomes unevenly distributed. You will see a lot of sudden decelerations and accelerations, and which is interesting because the road capacity is not changed. The number of cars is not changed. So basically the supply and demand is not changed. But traffic congestion happens because of these human-driven behaviors. Okay, so now I'm going to answer this question, why CEV, connected autonomous vehicles? So firstly, for connected vehicles, if vehicles are all connected, then it is capable of sensing the traffic conditions changes nearby in real time with the help of well embedded sensors such as LiDAR, radar, or cameras. And after sensing these little changes for the traffic conditions nearby, for example, this car's deceleration, acceleration, position, and the steering angle, things like that, and then this car will perform its autonomous vehicles feature to adjust its own speed and the accelerations accordingly. Okay, so back to the computer science area fully. This is an interesting simulation-based work using the well-known open source simulation of urban mobility, SUMO for short. On the left-hand side, you will see the simulation study to replicate the field experiments that you see in the previous slide. All cars are human-driven vehicles, and at the beginning, they're all evenly distributed, but after quite short amount of time, then you will find most of them suddenly change their speed, stop suddenly, and start suddenly. So lots of sharp acceleration and decelerations. And you will see these congestions happen from time to time. And what's interestingly, after introducing only one autonomous vehicles, the author of this paper using deep reinforcement learning model to train this car to while adjusting its own speed and acceleration, these accelerations just according to the gap between these preceding cars. So what's the result? Well, at the beginning, the so-called phantom traffic jam still occurs, but it is very smart because the goal to train that is to stabilize the whole traffic, to trying to reduce the sudden change of the speed. And that you can see that, well, very quickly, the whole traffic waves has gone. So this is why we need CEV in the near future to stabilize the urban traffic. Okay, so we've seen in the literature that CEV from simulation study and also from partially field experiments that CEV has the great potential to alleviate the recurrent traffic congestions. But how about non-recurrent urban road congestions, which is closely related to the resilience level of the urban road network? In this summer, we did a simulation-based study using the same simulator with two students from BDIC, Beijing Dublin International College. This is our collaborative college in Beijing University of Technology in China. And this work is also supported by another member of our Earth Institute, Dr. Beatrice from School of Civil Engineering. What we did is basically we close the road in the center. We close the road in the center. And for this scenario, we don't use CEV. For this scenario, we use CEV. And you can see clearly that after closing the road in the center, the whole network's average speed is quite low. And after applying CEV, the whole scenario average speed increased significantly. We've done a similar study in a much larger grid map. We're still doing the same thing, close the road in the center, and we see without CEV, you can see that this average travel speed is degraded in this surrounding. By using CEV, we can see this kind of impact is almost gone. Lastly, we also choose part of the city center in Dublin, and we did the same thing, but we mainly closed the 3 bridges in the city center. And after using CEV, we can see clearly that this average speed has been increased. More details can be found in this very early work. We still need to do a lot of work to develop it. And we've done fuel consumption, CO2 emission, and TTC, which is the used metric for measuring traffic safety. And also we've tested penetration rate, which means that, for example, in a small grid map, only the small portion of CEV can increase the travel time, can improve the travel time largely. And with the greater testing scenario, we can see more CEV, the better. Okay, that's all from me today. I hope you enjoyed this short talk this morning, and I'll be available for answering any questions you like. And also I'll be happy to initiate any chat offline if you're interested in collaborating with this interdisciplinary topic about sustainable and resilient traffic.
Brilliant, that's great. Thank you very much, Shen. I really enjoyed that. I've got a couple of questions I'd like to ask. If anybody else has any questions, please feel free to type them into the chat or let us know. So I'm a big fan of, you've converted me, I'm a big fan of CAV. You got me from the very first animation of the cars driving in a circle. I was going, oh my God. Like, that's like so many times I've been on the motorway and everything slowed down and then everything speeds up again and there wasn't any traffic. And I'm kind of going, why did we all slow down? But, so one thing I wanted to ask about that, you showed this great little video footage of the cars driving in a circle, and that was human driving. Was that actually a simulation of humans driving? Was that the sumo humans, or was that actual people in real cars? Now, if you go back one more slide.
Yeah, that's a real car and real human.
They're real cars and real humans. Brilliant.
Yeah,
I love that clip. That's very funny.
And you can see the cars are actually different.
I noticed they're different sizes, but I couldn't figure out if it was just computer graphics or if it was real. I really like that. That's fantastic.
And you can also Google Scholar this the paper is a very well-known study. So and you can find a lot of more details about how they pick the different human drivers, but still keep a well-representative driving behavior level of human. Yeah.
That's great. I've forgotten, Will, are the slides usually circulated for these afterwards?
We make the recording available, so we'll have that up on the Earth Institute website afterwards.
Great, great. I'll go read up on that that paper. It sounds fantastic. But for your own work, Shen, then when you shut down the 3 bridges in Dublin city centre, which sounds like total chaos, you showed that the CAVs responded much better. So the CAV, I understand, is a vehicle that can sense what's around it and it can adjust its own speed. But I'm guessing then it must also be linked into something like a vehicle routing program or Google Maps. Is that right, to be able to know the road structure?
Yes, but this is something we already have now. So we want to emphasize on the kind of exclusive feature that only CEV have.
Yeah.
So
in the human version of, so in the left-hand side of this, were they all human-driven vehicles that were all linked to Google Maps, let's say? And the right-hand one were the CAVs linked to Google Maps. I
think actually in this very early simulation study, it doesn't actually matter, because what's matter for this assumption is if all the vehicles linked to Google Maps, they can reroute themselves smartly, right? But in this simulation setting, we don't consider a smart rerouting so far. What we did here is, after we close one road, so for the vehicles that's supposed to go through this road, they will recompute their routes only according to Dijkstra's algorithm, which is choose the shortest distance route. which means that, okay, well, you can use Google Map, but you cannot use Google Map traffic.
Yeah. Okay. Excellent. Yeah. That's what I was wondering. How much of the kind of Google Maps prediction of where the traffic goes would be in this? But if you don't have the traffic on it, then it is a much more simpler vehicle routing problem.
Yeah.
That's great. Thanks. I just had one more question. I really liked your graphic explaining the difference between making an efficient road network and making a resilient network. Presumably cost needs to be taken into account here at some stage. Do you have any idea, how people make those decisions? So if you have to make a resilient road network, you need to physically build more roads. Do people do it just to increase resilience, or do they just kind of naturally grow to be more resilient?
For these kind of things, I think maybe it's better to forward your question to my colleague Beatrice. So she's an expert in building resilience transport network. So because I'm from School of Computer Science, so my research focus is trying to use ICT methodologies, information communication technologies, trying to make the existing road network react to this sudden change of traffic more quickly. But in terms of rebuilding the whole network, I think it requires a lot of investment. So I think for people from the School of or civil engineering area, they have more specialized tool to simulate it, and also they have their own channel to communicate with authorities and companies who want to make this investment. Yeah,
that's a very good response. You should be a politician. But actually, what the Earth Institute are trying to do, I think it could be great potential for interdisciplinary work. If they're doing this work and trying to optimize resilience, but they're not taking the next generation of road vehicles, CAVs, into account, then obviously it's a nice piece of collaborative research if we can try and include the projections of how our vehicles will behave in the future, along with policy making decisions about how we should make our infrastructure more resilient. Sounds like a nice future area, perhaps, for some collaboration. Okay, just one more in an audience question. Do the level of automation in CAVs have an impact on road traffic safety? So our more modern level 4 CAVs, are they better than level 2 CAVs in improving safety and efficiency?
Very good question. So in our early stage simulation study, we use a kind of car fault model to mimic level 4. So all CVs we consider here is level 4 autonomous level. So so level 2, to the best of our knowledge, we haven't found a good simulation model to do that. But maybe for level 5, it is even more complicated because you need to gather a lot of informations, visuals or non-visuals happens in the surrounding of the cars to make decision. But level 4 is achievable now in Sumo. Yeah, we use level 4. Yeah.
Great. There's Liz Bruton has a hand up. I'm not sure, do we need to allow people to speak, or?
Oh, I think that's fine. Yeah, Liz, if you're there.
No, really, really interesting presentation. I was just wondering, in terms of your simulation for bridge closure in Dublin, does it assume that suddenly they close and a number of human-driven cars on the road are exactly the same? Or does it factor in things like human behavior, i.e. if you announce that 3 bridges in Dublin are closing tomorrow, the numbers of people trying to drive into Dublin significantly decreases?
Yeah, very important question actually. So what we did in this simulator is that it has the kind of mimic way to simulate what's happening in the real life for rerouting, is that we put a kind of things like this. Sorry. Yeah, we put a thing like this, and after from the time that we put this sign here, the cars that are already on the roads that is going to be closed still can go, but the car that needs to go through, they have to reroute. And we don't simulate the scenario like we announce one day before, because that's kind of predictable solution. Okay. So which is not suddenly happen on the road, which does not require very timely response. So, you know, for CEV, for CEV, the connected vehicles, the existing communication protocol, the slowest update frequency is every 10 times every second. So this is kind of timely that we want. But for one day announcement in advance, we can still use some big data or AI technologies trying to avoid that, using Google Maps, for example. Yeah.
That's great. Thanks for that question, Liz. All right, well, if there are no further questions, I'd like to thank Shen again for a very interesting talk. And I certainly, for one, look forward to there being more CAVs on the record. Thanks very much, Shen.
Thank you. Thank you.